Let's try applying the HSAB theory in some of the phenomena in chemistry that we are familiar with. First, hydrogen bonding. For example, we have two molecules, acetonitrile and trimethylamine. Shown here are their polarities. Acetonitrile has a polarity of 3.44 d by units, while trimethylamine has a polarity of 0.7 d by units. This means that acetonitrile is more polar than trimethylamine. Let's say methanol forms hydrogen bonds between these two molecules. So you have a hydrogen bond between methanol and acetonitrile and hydrogen bond between methanol and trimethylamine. So the question is, which of the two hydrogen bonds is stronger? Is it the hydrogen bond between methanol and acetonitrile, or is it the hydrogen bond between methanol and trimethylamine? Make a guess. So if you guess that the second pair, the methanol trimethylamine, forms a stronger hydrogen bond than the first pair, you are correct. So nitriles, like acetonitrile, are soft bases, but amines, like the example here, trimethylamine, are hard bases. So alcohol is also a hard acid. Okay, so this means that the interaction of methanol with the trimethylamine is more favorable than the interaction of methanol with acetonitrile. And in fact, if we look at the values, the energy of the hydrogen bond between methanol and acetonitrile is only 6.3 kilojoules per mole, while the energy of the hydrogen bond between acetonitrile and between methanol and trimethylamine is 30.5 kilojoules per mole. Okay? Okay, let's try another example. So let's say we have diethyl sulfide and diethyl ether, and you have phenol forming a hydrogen bond between diethyl sulfide and also between phenol and diethyl ether. So which of the two will have the higher energy? So you have to ask. Let's classify. Ethers are hard bases. Alkyl sulfides are soft. From the previous example, we knew that alcohols are what? Soft or hard acids. They are hard acids, which means that the interaction of phenol with the diethyl ether is more favorable than the hydrogen bond of phenol and diethyl sulfide. In fact, when we look at the infrared spectrum of the phenol diethyl sulfide and the phenol and diethyl ether combination, and looking at the OH band, for the phenol diethyl ether mixture, the OH stretching band is shifted by 280 wave number. But for the phenol diethyl sulfide mixture, the OH stretching band is shifted by only about 250 wave number, which means that you have a stronger interaction between phenol and diethyl ether. So the energy of the hydrogen bond between these two is 22.6 kilojoules per mole, while the hydrogen bond between phenol and diethyl sulfide is 15.1 kilojoules per mole. Next, your HSAB theory in linkage isomers. So linkage isomers are found in your coordinate compounds, or what we simply call complex molecules or complexes. Again, this is in relation with the behavior of your metals with regards to the electronic character of the molecule donating electrons to them. So you have the class A and the class B metals, if you remember. Shown here is a platinum complex. And again, we observe that the sulfur atom of this base is interacting with the platinum center. It is also possible for the platinum center to interact with the nitrogen of this base. However, the one interacting with the sulfur is more stable than this one. So these two are what we call linkage isomers in coordination chemistry. Another example, so for a class A metal, so again you have a cobalt 3 as a class A metal. So in this one, you have a complex. So this cobalt center can also interact via the sulfur atom of the base. But this one, so let's complete the complex just for the sake of clarity. Then you have 5 NH3 molecules. And the charge. Okay, so these two are called linkage isomers in coordination chemistry. Again, the more stable complex is the one where cobalt is interacting with the nitrogen of the base. Next, HSAB can also be applied in the concepts of precipitation and solubility. So for example, say you have a solution. So you have cesium, lithium, fluoride, and iodide ions dissolved in water. And let's say you evaporated the water. So what do you think, or what are the solids that you will have after evaporating the solvent? Will it be cesium iodide plus lithium fluoride, or cesium fluoride and lithium iodide? So apply your HSAB theory. So we know that cesium is a very large atom. So cesium ion is large, therefore it's a soft acid, while lithium ion is a hard acid because it's small. Fluoride ion is also a hard base, while iodide ion is a soft base. So, which is more favored? It would be the cesium iodide and the lithium fluoride compounds. Again, because your hard, soft interactions are more preferred over the hard, hard interactions. Next, HSAB can also be used to explain your organic reactions. So for example, you have a nucleophile such as thiocyanate reacting with your methyl iodide or an acyl halide. So the thing is, an acyl halide is considered a hard acid, while your methyl in the methyl iodide molecule is considered a soft acid. This means that we can classify methyl in methyl iodide as a class B metal. It's not a metal, but we can put it in the class B, and acyl halide can be placed in the class A. And this means that this nucleophile, the thiocyanate, will react via the sulfur atom if it attacks the methyl in methyl iodide, but it will use the nitrogen atom if it reacts an acyl halide. Another example, there should be another example here for your organic reaction. So the second example is the reaction of nitrite ion with methyl iodide and tert-butyl chloride. Okay, let me write that down. So you have a nitrite ion reacting with a methyl iodide and also reacting with a tert-butyl chloride. Okay, so again, methyl in methyl iodide is considered a soft acid. So this means that you have nitrogen, okay? This time it will be nitrogen reacting with your methyl because the other option is oxygen. But oxygen is harder in electronic character than nitrogen because it's more electronegative, right? So for methyl iodide, which is a soft acid, the methyl group in methyl iodide, which is a soft acid, it will be forming CH3NO2. So the nitrogen from nitrite ion will be the one attacking. But third butyl chloride is considered a hard acid. And for this one, it will be oxygen that will be attacking your third butyl chloride. Again, because oxygen is harder in electronic character than your nitrogen atom. So your product would be, so first you will have a third butyl carbocation because the chloride ion will leave, or it is your leaving group, and you have an oxygen atom that is bonded to your third butyl carbocation. So you have there um, this one just to represent the oxygen interacting with your butyl group. Okay, so those are some phenomena that can be explained using your HSAB theory.